We're now ready to prove the main theorem of this lecture. Basically, this curly L1 is a complete vector space. Okay, so when you want to prove something is complete, by definition, you need to show every Cauchy sequence converges. And the standard trick is in the metric space, you can just, by dropping down to a subsequence, you can just assume the distance between the two elements, Fn and Fn plus 1, is bounded above by, say, 2 to the negative n. And because we're in a vector space, it's actually, we can even drop it even further. So it suffices to prove the following. So if I have a sequence of L1 function, here Fn come from the curly L1, and their one norm is less than 2 to the n, then their sum is actually inside this L1, the curly L1 as well. So the infinite sum, which is, I use this notation, is really just the limit of their finite sum. We know L1 is a vector space, so finite sum is in there. So we just need to show this sequence, this finite partial sums, they have a L1 limit, okay? So you can convince yourself why this is enough to show this vector space is complete. Okay, this is a quite standard trick. I'm not going to talk too much about it. All right, so let's prove this claim I have here. Okay, so first of all, I want to invoke the Lebesgue dominant conversion, so I need to find something that bounds each one of these partial sums. So how about let's give the partial sum some name. Let's call it big Fn. Okay, so this is the nth partial sum. We know they're coming from L1 of mu. And what's the common upper bound of these Fn? Well, you can just take the guess. You let G be equals to the summation of all the absolute value of Fn. Okay, so maybe I should say K here. So K going from 1 to infinity. And I first need to show this G is indeed an L1 function. Okay, so here G is just a countable sum of some non-negative function. Each of these Fn absolute value is non-negative. So we already saw the integral of non-negative functions is satisfy this countable additivity. So this is just equals to the summation, okay, going from 1 to infinity of their integral. Okay, so Fk d mu. And this is no other than the one norm of the Fk, which is bounded above by 2 to the negative k. Okay, so everything is bounded above by 2 to the negative k, and here k going from 1 to infinity. And you can see this is just equals to 1, which is certainly less than infinity. Okay, so I have this as bounded. Okay, so this G is indeed inside L1. Okay, so here you may see I use the curly L1. Let's just pretend G, well, G is technically just a L1 function, but let's pretend it's inside the quotient as well. And by the way, I just noticed when I read Ken's course note, his course note a little bit messy between this curly L and the normal L. Okay, so he introduced his the L1 in the first section as the integrable function, and then in the second section he used the same L1 as the quotient. Okay, so in my course, the curly L is always the quotient. Okay, the normal L is always the non-quotient. Okay. All right, anyway, so we find a G, which we think it should dominate Fn, so let's better check that. Okay, so I have, by definition, the Fn. Okay, so let's consider its absolute value. So it's the nth partial sum, so k going from 1 to n of these Fk. And we have the absolute value satisfy the triangle inequality, so this is just the nth partial sum of the absolute value, so it's certainly less than or equals to G. Okay, G is the G has adding more tail, so everything is non-negative, so G is dominating all of these big Fn. Okay, so we're in a good shape setting up a dominated convergence. Okay, so let's first of all we actually need to show that these Fn actually converges somewhere. Okay, we need a candidate where it converges to. Okay, so because these Fn are dominated by G, and because G is inside the L1 space, so G is inside L1 of mu, we can actually show that Gx is finite almost everywhere. Okay, if it's not finite, if it's infinite on a non-measured zero set, then the integral has to go to infinity. Okay, g is a non-negative function here. Okay, you can convince yourself why that's the case. Okay, so g is almost everywhere finite, and that will imply, because I have this dominated, this Fn is dominated by g. Okay, this is just by how it's actually defined. So we actually have that the summation of k going from 1 to n of these fk of x. So if you fix on x, okay, and you consider this sequence, okay, so that's almost everywhere is going, well, first of all, it's always dominated by g of x, but almost everywhere is less than infinity. So because this g doesn't depend on n, so I can say this this series of fk absolute value, that's finite almost everywhere. Okay, so because you have the summation of the absolute value less than infinity almost everywhere, so from your math 148, you should know that this is absolute convergence will imply the series itself converges. Okay, so I can just let f of x equals to the summation k going from 1 to infinity of, let's take it without the absolute value, that actually converges almost everywhere. Okay, because almost everywhere is absolute convergence. Okay, so because the absolute convergence will imply convergence. Okay, so this is from 148. All right, so anyway, so now I have a candidate of this function. So this f of x is certainly equals to the limit of these fn of x almost everywhere. And if the g of x is infinity, okay, so it's only infinity on a null set. So let's just define it, give a random value for f. Okay, we can just say define it as 0. Okay, so here just a note, we can set f of x equal to 0, or really any function, any value you like. Okay, so a null set doesn't really matter. Okay, so if g of x equals to infinity, so because on that set the Fn may not converge absolutely, so let's just give some value. All right, but anyways, these Fn, this big Fn will converge to this big F pointwisely almost everywhere. Fn is dominated by G, so by the Lebesgue dominated convergence, okay, so Lebesgue dominated convergence theorem, it tells us, first of all, the integral of these Fn d mu will converge to the integral of f d mu, okay? So that's first of all. And in fact, the integral of the absolute value of d mu is also equals to the limit of the integral of these fn d mu. And again, each fn is dominated by g. So this is dominated by the one norm of g, which is less than infinity. So here I have this big F is going to be inside the L1 space, okay? All right, so we now have a pointwise limit of the sequence Fn, okay? I'm only having a pointwise limit of Fn. We want to show that this big Fn converges in the L1 space, okay? So the pointwise convergence, even though this pointwise limit is an L1 function, we haven't proved that this is actually the L1 limit of the Fn, okay? So we need to show the following. So we need these Fn actually converges to F in the L1 space. And let me remind you, the L1 space, the distance is defined by its norm, okay, the one norm. Okay, so in other words, what I need to prove is that the integral of their difference, okay, so this is Fn minus F, okay, so this one is going to 0, okay, so, or in other words, their one norm, the difference between Fn and F, their one norm is going to 0, okay, so that's what I need to show, okay. Well, to show that, well, we can again apply the dominated convergence. So this is very simple. So here Fn minus F, well, we know is converges to 0 almost everywhere, okay, pointwisely. And the Fn minus, let's to minus NF, the absolute value is bounded above by the Fn absolute value plus the F absolute value, okay, absolute value, not norm. Okay, but both Fn and F are bounded above by the G, so it's bounded above by 2 times the G, okay? Well, G is L1, so 2 times G is again L1, so that's fine. Okay, so we're again in the dominated convergence setup, so the big dominated convergence theorem tells me that the integral of their difference, the absolute value of their difference, okay, that's going to be converge to their limit, okay, the limit is just equal to 0, so it converges to 0, okay. So this, we can conclude my sequence, the partial sum Fn, converges to this pointwise limit in the L1 norm, okay. So in other words, the L1 space is complete, okay. So we finish the proof.